Hi, everyone. Thank you all for joining us today, and welcome to Steam Management's webinar series. In this session, we'll be focusing on developing Steam system ECMs for performance contracts. Leading today's discussion is Chase Bean, our Vice President of Revenue and Engineering. Chase is a licensed professional engineer in multiple states with more than 16 years of experience in the energy sector. His work at Steam Management includes supporting ESCOs and navigating the EPC process, combining technical and project development expertise for today's discussion. You're welcome to ask questions in the chat at any time. We'll try to address them during the presentation, and we'll also save time at the end for a Q&A. Thanks again for tuning in, and now I'll hand it over to Chase to get the presentation started.
Thanks, Ashley. Yes, so we're Steam Management. We provide turnkey retrofit projects with a focus on efficiency improvement in Steam systems. Frequently, we are doing these for performance contracts, which is why we're talking about energy conservation measures for performance contracts today. And our solutions include reduced system energy costs, conserving water, and reducing carbon footprint. I would like to point out, too, if you need a PDH certificate for today's webinar, our process for that is to email me at cbean@steammgt.com, and then we'll get that right over to you for completing the webinar. Learning objectives today, we're going to recognize some key indicators of high-value Steam ECMs during walkdowns. We're going to understand what data is most important to gather for savings evaluations. We're going to apply best practices for qualifying Steam opportunities early in the project lifecycle, and we're going to align preliminary findings with the requirements of performance-based energy projects. As an overview, we'll look at some common efficiency opportunities. So, although the puzzle kind of changes from site to site and project to project, these are some of the common efficiency scopes that we see over and over again. On the distribution side, it's keeping steam traps maintained, using TRVs for controls, and insulating lines. Those all cut losses and improve comfort. And then fixing leaks and lowering pressure where possible is also a quick way to drive savings. Removing abandoned lines, improving condensate return, and adding heat recovery also reduce fuel, water, and chemical use. And then optimizing boiler operation and using VFDs on pumps and fans can help match the output to demand and save some electricity as well. So these opportunities can often be identified early in the development through walkdowns and surveys. Here's kind of a take on the ESPC life cycle and where walkdowns and surveys fit. I know this isn't the exact framework for every ESPC, but just kind of a general progression. So often in the proposal assessment phase or RFP phase, we're going to do some walkdowns. Like I said, it's a case-by-case basis. Sometimes we know there's an opportunity there, and we're going to do basically a full-scale survey. Sometimes we're doing testing a sample of traps or surveying some of the system for just rough order magnitude insulation scope. For equipment replacement opportunities or heat recovery opportunities, those kind of things, we're looking at maybe 30-60% engineering design just to kind of start the development of a scope. And then once the proposals are down selected and we move to investment grade, then we're going to do detailed audits. If we didn't do it during the proposal assessment, we're going to take that engineering to, we'll say 90%, but whatever level is required to really firm up the price for a turnkey installation and firm up savings. And often that's going to involve walkdowns with our installers and maybe even walk in the same system again, but with more people involved. And then obviously we get involved. We're providing turnkey projects, so we're obviously involved in the contracting and construction and M&V phases. But for this discussion, we're mostly talking about project development and scope development. So we're looking at these green phases here. Now we'll talk about pre-walkdown. This is basically planning and what information we need. So talking about what to request and why, and I'll go through these in a little bit more detail, but plant and equipment data, utility bills, drawings and controls, prior assessments and test reports, operating snapshots or trends, and constraints and safety requirements. So plant and equipment data, I won't read all of this, but basically all the major steam system equipment is useful. But at a minimum, we really would love to have boiler and burner nameplate data, photos, as-builts, and age of equipment, maintenance history, any notable upgrades. These are all useful pieces to have. Obviously, like any scopes, we want utility bills. In our case, we're generally concerned with fuel, water, and electricity. Makeup water volume and treatment costs are also helpful. And then like makeup and feed water quality reports can help us determine blowdown flow rates and things like that. And then water treatment logs, like if you can get your hands on the operator logs in the boiler room that show like water treatment measurements and things like that. We also request key documentation such as P&IDs and layout drawings to understand the system, a PRV station list, and BMS screenshots with trends or operator logs and pressure measured process parameters so we can focus our time in the field where it matters the most. And that's basically what all these are talking about. And we want to get the most out of our walk down, so we want to kind of get as many clues as we can ahead of time. We'll also look at prior assessments, things like steam trap surveys, installation reports, combustion tests, or broader system and energy engineering assessments. Those give us a good baseline, helps us avoid like repeating work, and kind of steers us towards maybe opportunities that have already been identified, but just not followed through with or not further developed. Operating snapshots are great. Basic loads, pressures, temperature, stack temps, O2 measurements if it's available, along with operating hours, seasonal modes, any known problem areas or alarms. It gives us a good picture of how the plant is currently operating, and maybe we can start putting together what opportunities may exist before we even get to the site. And this is not just for us. I mean, these are good. The intention here is to show you what maybe you can look at as well when you're developing performance contracts. We also plan around the constraints and safety, so things like access timeframes, available escorts, and access limitations. Are we on roofs, tunnels? Do we need ladders? Are there confined spaces that we need to account for? And then what is like the safety orientation, safety requirements before we get on site? Any questions on this pre-walk down information? Okay. Walk down game plan and tools. So this is kind of how we approach our walk down and what we will bring with us. The game plan kind of depends on a variety of factors. It could, based on the type of facility, the type of assessment, the information that's already been provided, and kind of the clues that we already have and what we think is going to be pertinent to look at. For most surveys, we're going to start at the boiler plant, so steam trap surveys or installation surveys, condensate pump, whatever, leak surveys. We're going to start at the boiler plant and follow the steam and condensate lines away from the plant. For a systems assessment, we're going to spend kind of the same. We're going to spend a lot of time in the boiler plant with the generation equipment, and then follow the steam lines out to the end users that we're wanting to look at anyway. We don't necessarily, if we're doing like a system assessment, we don't necessarily walk every single line like we would with a steam trap survey. But basically, our goal is to capture as much data as possible while we're there, and then sort it back out when we get back to the office. Hopefully we have a lot of information up front so we can target our efforts, but we collect all the data that we can, and some of it will prove useful once we get back in the office, even if we don't know if we need it while we're in the field, right? Tools for a first pass for us, we're usually going to have an ultrasonic probe, even if we're not doing a full-on trap test. It's helpful to be able to spot check traps if you see a piece of equipment that's having issues. You can also check like steam motive pumps and pump traps So those ultrasonic probes can be very useful for a variety of things. Maybe even more important on a first pass, if we're not doing a trap test, is an IR camera or a gun. Can be a really good kind of cheat that that I can use. Like if I walk into a boiler plant and I have my camera, I can turn my camera on and scan the room and just see what's on and what's not on. You can immediately see insulation deficiencies. You also, just the nature of steam, right? Like if you know the temperature of a line, you know all the other properties of the steam. So that helps us put together a heat and mass balance, run calcs, which we'll talk about more later, but just really helpful to have the IR camera. And then also we use that as a backup test for steam trap testing, which we'll talk about as well. Measuring tape laser or measuring laser, that's just for, obviously measuring like lengths of insulation if there's missing insulation, or what's the available area for a potential equipment retrofit, right? Flashlight, phone, tablet, paper tag. So we often tag equipment, especially like on a steam trap test or survey. We're going to tag a lot of the traps, at least in the mechanical spaces. We'll usually do that unless the site already has a pretty good tagging system. Here's some opportunities found during walkdown. So yeah.
We have a question about the last slide. It says, are there
Okay.
any data logging equipment that you typically use for baselining or trending?
So sometimes, yeah, I feel like a lot of times we're kind of beholden to what the plant has. But luckily, like I said, I'll talk about a heat and mass balance later, but there you can kind of model out what the system looks like and use utility bills to get a good picture of the system. And hopefully they're measuring some stuff, right? Like, so if you have steam flow and they're measuring condensate return, then you can calculate makeup water. Or if they're measuring makeup water, you can calculate condensate return. So I don't know. I mean, have a permanent meter installed, but we definitely also have put in meters as part of establishing a baseline. So kind of a non-answer to your question, but it's kind of a mixed bag of how you want to approach that. Okay, so steam traps are usually an opportunity. I want to make that clear. If there are yearly failures, so if you have a steam trap population, you can expect 5 to 10% of those traps to fail every year. Traps are designed to fail open, so that they will still reject the condensate from the system. And so when a trap fails, I mean, it's possible that they fail closed, but 90% of the time they're failing open. And then you're having basically a hole that is just constantly blowing steam. You're paying money to generate this steam and to treat this water for the boiler system, for the steam system, and then you're just blowing it out of a hole and it's escaping through the vent in your condensate collection tank. So it's a total waste. There's low maintenance visibility. So like this is the steam trap in this picture. And the point of this picture is to convey, like, you see all these cobwebs and everything. Nobody's looking at this. Nobody's testing this. It's, they can easily go unnoticed for a while. Also, like by nature or by design, rather, they're made to fail open. So a lot of your equipment will still work with a failed open trap. Now, it will cause issues as far as back pressure on your other radiators, and other issues downstream, water hammer, and all those things. But generally speaking, sometimes the equipment still works and it kind of goes unnoticed, and it's just unnoticed energy loss. So there's good potential for savings. It's direct measurable savings. It's fairly easy to calculate the energy loss from the failed traps. There's usually access to incentives from repairing those traps, and then there's added side benefits like mitigating water hammer and reducing maintenance requirements and things. The other thing to note here is trap surveying is an opportunity multiplier. So this is a great first step for us into the development. When you survey steam traps, you are seeing the whole system, basically every foot of piping in the system. We're walking it down and seeing it. So we're going to see leaks. We're going to see insulation deficiencies. We're going to see heat recovery opportunities. And this photo here is just kind of conveying like who's going down that tunnel on a regular basis to see if there's a leak down there, right? But we are when we're doing a trap survey. So it is just a great first step when you're doing the development to identify other opportunities as well. Next opportunity is insulation. Basically, any hot equipment that doesn't have insulation and it's appropriate to insulate it can be an opportunity, and we'll kind of go into a little bit more detail on that later. Condensate return. Condensate recovery is critical because basically you're returning hot treated water back to the boiler house. So every bit of condensate recovered represents less cold makeup water needed for the system and the associated heat required for that makeup and the treatment chemicals required for that makeup, as well as the water cost itself. So any condensate return, mitigates all of those losses and also reduces the deaeration load on the deaerator, reduces boiler blowdown because now you have less dissolved solids being introduced to your system through the makeup water. So it is critical to return as much condensate as possible. I see a question there. Can you find appropriate to insulate? I do have a slide later where I kind of call out some things that maybe you wouldn't want to insulate. So I will get to that question. So we look to recover flash steam instead of vent it. We upgrade or add pumps where needed to keep condensate moving. Try to stop condensate losses to drains is a common thing you'll see where you have a user using steam and they just dump the condensate to a drain, which can waste energy and water, but also can damage sewer systems. So also can optimize your piping layouts or the piping layouts, add or restore pressurized return systems or pump traps to kind of help boost that condensate and get it where it needs to go. So yeah, there's a lot of things you can do to improve condensate return. End use opportunities. There's so many different things that could apply to this, but one big opportunity I did want to highlight is the retrofitting or replacing thermostatic radiator valves. They're basically little control valves that replace the manual valve on a radiator or fin tube, and they react to the temperature in the space and regulate steam flow to the radiator. So they can really save a good amount of energy. I think 5% of that particular radiator's energy use is a typical rule of thumb. So those are a good opportunity and also a good tack on for if you're doing steam trap retrofits anyway. Other end use opportunities can be like if you're thinking of the actual equipment itself, replacing or upgrading inefficient equipment, or correcting overheating or condensate return issues like from the equipment, like I mentioned, if that piece of equipment is discharging condensate to drain, you can address that. PRV stations. So these are another common source of efficiency issues. We often find set points aren't optimized compared to actual pressure drops. In some cases, the bypass valves get misused as control devices. Noisy pilots or poor modulation are clues to underlying problems. And then there's missing or failed drip leg traps. And often you'll see like a bucket trap downstream of the PRV, which is not a good application because bucket traps require a primer of water. And downstream of a PRV, you get a little bit of superheat in the steam, and it will evaporate that water out of the bucket trap, and then it will fail to work. So there's just a lot of problems that occur around these stations, and often there's an opportunity for efficiency improvement. Combustion health. So when we're looking at boiler combustion health, we're looking at a few key indicators. Stack temperature compared to feed water gives us a good sense of how it's operating. You have O2 or excess air readings. which you can do through combustion testing. As a photo there of a combustion analyzer from just recently, from a test we did just recently, and then watching burner turn down and control behavior tells us how the boiler's operating, and especially like across its load profile. Are there heat recovery opportunities? Now, these are not always, this is where like the inputs to the system equation can vary how, attractive these opportunities are, right? Like, is there an economizer? Is there an opportunity for an economizer? Is there an opportunity for a combustion air preheater, blowdown heat recovery? And I should mention, like with an economizer, basically a rule of thumb is a 1% efficiency increase per 11 degrees of feed water temperature increase. And basically what an economizer is this. So it's a heat exchanger in, when you talk about a boiler economizer anyway, there's plenty of different types of economizers, but generally when you're talking about a boiler economizer, you're talking about a heat exchanger in the flue gas stack that is heating some process. Typical application is preheating feed water before the boiler. So basically here you see a boiler with a feed water economizer, and here's one without. And these are actually in the same boiler room. And as you can imagine, the one with the feed water economizer is the primary boiler, and the one without is a backup boiler. And that's something to look at when you're looking at these opportunities, because I often get excited when I see that there isn't an economizer, but a lot of times there's a reason for that. Like he's got low run hours, or whatever, and it's just, there's a reason that they don't have an economizer. It wasn't worth investing in, and maybe it's still not. But they also often can be an opportunity as well. Combustion air preheater rule of thumb, 0.5% efficiency per 20-degree combustion air temperature increase. You don't see that as much with like these fire tube boilers, but you start getting into larger boilers, and preheating the combustion air can make a big difference. One thing that you will see with these types of boilers is you can actually, if you're in a boiler room that has a high ceiling and it's pretty hot in there, you can pull your combustion air intake from the roof to get hotter combustion air. Not from the roof, but from near the ceiling, where it's kind of stratified up there, and get hotter combustion air and get some efficiency gain. I got a question here on long piping tunnel runs, difficult to access. Is the baseline system modeling protocol precise enough to potentially identify hidden steam or condensate water leaks? I guess I don't know exactly what you mean. It's a baseline system modeling protocol precise enough to potentially identify a hidden steam or condensate water leak. You certainly could have, like, so if you model out like a heat and mass balance, or even for just that portion, and it's not hitting the performance that you would expect it to hit, that certainly can be an indicator that there are leaks. But yeah, I mean, I guess it's a case by case basis, like how confident you feel in that, how accurate that is. I don't know if that's answering your question, but some other heat recovery opportunities, blowdown heat recovery. So blowdown is as steam evaporates in a boiler, it leaves behind dissolved solids. I talked about this in other webinars, but so I won't go too far into it, but basically you have a stream of blowdown, a surface blowdown or continuous blowdown out of the boiler that removes these solids from the surface of the boiler. And so that's just like a wasted stream of saturated water. You're heating that water all the way up to boiler pressure and boiler temperature, and then you're just rejecting it down the drain. And so you can recover heat from that. You can recover flash steam from that. And it's a great opportunity. Like I said, if you have enough blowdown to make it, a good savings. And that's often driven by the water quality, as well as the other common inputs like operating hours, fuel costs, etc., water costs. For heat recovery, we're often vetting those out through the development of a heat and mass balance for the system. So this is one we did just recently. And basically you just have a bunch of different flow points here, and you can see from the blue fields are the input fields. So just with some collected data and using the properties of steam and balancing steam flows, you can really kind of model out the whole system. So this is what I was talking about earlier. Like if we have makeup water flow, maybe we can determine what the expected condensate flow is. And you have to make some assumptions here sometimes to finish it out, but you can get a pretty good idea what's going on. You can run different cases, summer case, winter case, or just 25, 50, 75, 100% load, something like that. And then you can plug in pieces of equipment like a blowdown heat recovery or something and see what the impact on the system is, because some of these savings are, pulling away from other savings, right? So I don't know. It's a really good tool for us to help develop scopes. Then there's also makeup water and deaerator improvement opportunities. We're evaluating, is the makeup water rate what we would expect? And then is the DA pressure optimal? Is it venting appropriately? And then these photos are just like this is a water quality analysis. And this is where we were able to take boiler logs of feed water flows, boiler operator logs, I should say, feed water flows and condensate return, and model that out and kind of see what we were looking at. This is a deaerator here. This is the vent, and this is a well-performing deaerator. The vent is just kind of wafting steam, and that's what you would expect. Really, the point of the vent is to be able to reject the air that's being removed from the steam or from the feed water, and it shouldn't be blasting steam out unless you just have a lot of makeup water, I guess, and a lot of air to remove. All right, this section is called clues. So I'm going to talk about some of the general clues that we'll see that there is an opportunity, and then how they're applied, or maybe more specific to each opportunity. And trying to focus on contract driving scopes. And by that, I mean not necessarily facility needs, but scopes that cash flow well and will often get included. General clues, some of these are probably pretty obvious, but high utility rates, if there's no existing or poor metering, high water use per unit of steam demand. If the system just has older equipment, right, that means any amount of steam or heat that we save is then multiplied by the poor efficiency of the system as far as the fuel cost. If you have a large distribution system, you're likely to have abandoned sections, piping leaks, insulation deficiencies, also likely to have a large steam trap population, and then that multiplies, the number of failed traps and the opportunity there. And then if you have high makeup water rates or low condensate return, that's usually going to indicate that there's condensate return improvements, or just that there is a low system efficiency, and it's in your best interest to try to conserve some steam. Other clues: missing or damaged insulation, PRVs making big drops or cascading PRVs. If there's indication that there's water hammer, piping vibration, rattling, high stack temperatures, high excess air, a lot of short cycling in the boiler. There's no economizer. Again, we talked about blowdown, so that there's a high blowdown percentage. Maybe you see that there's a manual surface blowdown present, and that there's no blowdown heat recovery system. That could be an opportunity. Also, another general indicator is if the controls are left manual, so you have bypasses cracked open, there's no niter we can set back, and pumps are on constant speed motors. All right, here's some examples of a clue and then what the ECMs could be. So high stack temperature could be an economizer or a condensing economizer. Large PRV drops with tolerant loads could be a pressure reduction opportunity. Bare mains, valves, PRVs, insulation retrofits, trap failures, obviously going to be test, repair, monitoring for the steam traps. Receiver vent flash could be trap repairs, could be return improvement, could be a vent steam recovery, heat recovery opportunity. High O2 or poor turndown could be combustion equipment upgrades. And then large blowdown flow or poor makeup water quality could be a blowdown heat recovery, could be upgraded water treatment, could be condensate return improvement. All right, so for the steam trap ECM, here's the clues here. And the number one clue is that there is no active trap maintenance program. So traps fail every year. Like I mentioned, you're going to lose 5 to 10% of your traps every year. If they're not maintaining their traps every year, every 2 years, there's going to be a significant amount of traps failed, and there's probably an opportunity there. If they have a decent quantity of traps, then it's a a scope worth looking at. And then all these other things are indicators as well. One thing to point out that's kind of easy to identify if there's excessive condensate tank venting. So if you go to a steam system and you're seeing their condensate tanks or even vents on the roof of just steam billowing out, that means they probably have some failed traps, and there's probably an opportunity there. Here's an example of a trap opportunity. So the system conditions where we had a central heating plant with multiple boilers supplying 23 campus buildings. It had an aging steam distribution system with leaks, poor insulation, and years since the last trap repairs. And then there was significant steam loss impacting energy costs and reliability. The approach was to perform an investment grade steam trap survey. We used ultrasonic testing, thermal imaging, and visual inspections to identify failed traps. And then the trap survey provided visibility across the entire steam system, leading to the development of additional ECM scopes like insulation, PRVs, upgraded heat exchangers, and condensate return improvements. Example savings: we replaced or repaired 227 failed traps and installed 19 vacuum breakers for an annual savings of 6,000 M-pounds per year, which is a $40,500 annual value. And we have some typical installed cost here. So the low end is like a 2.4 year payback or 3.6 year payback, from our cost. So that's a pretty good scope. As for insulation, the opportunity example here is, not example, the clues here, I should say, are bare or failed insulation on hot piping and equipment, especially larger bore equipment. So this is kind of your hierarchy of priorities, right? Like you got your valves, PRVs, strainers, and flanges. Those are a priority because they are a lot of surface area for the amount of insulation required. And then tanks and large bore piping and fittings are going to be a better payback than small bore piping and fittings. And the reason for that is, again, it's the surface area compared to the amount of insulation and the labor required to install that. So if you think about a small bore pipe and the amount of surface area on a small bore pipe compared to the amount of insulation when you're putting an inch or two of insulation around it compared to a big tank or a large pipe, it's just a higher ratio. So this is kind of the hierarchy of payback here. And the clues really, I mean, like you said, it's bare failed insulation. Hotter systems are better, which is why this is a great opportunity for steam systems. I would say the payback's generally going to be better on a steam, condensate, hot water, thermal oil even system than it is going to be on like a chilled water system. And that's because of this temperature differential here. And this is your heat transfer equation, right? And everything else being equal, that larger delta T between a hot steam system and the ambient environment, it leads to a lot of savings potential. Again, long run hours are good. High heating costs, so the poorer efficiency the system has, the better payback insulating it has. And then you're going to prioritize the opportunities by, the delta T times the operating hours times the surface area times the cost of heat, right? So, the output from our survey is, or for a mini installation survey, should be line by line application schedule with the opportunities listed, and then you can prioritize those with quicker payback. So you don't necessarily insulate every single thing that was identified. Although in steam systems, most things are hot enough that as long as they are operating like a significant amount of the year, it's going to have a decent payback. There are some things. So somebody asked earlier. So there are some things that you should leave bare. So this is what's called a low profile condensate receiver with electric pumps. So you see, this is kind of a short tank with a pump mounted on the side of it. There's very little NPSH available, net positive suction head available, which is basically the height of liquid upstream of a pump, right? And so in steam systems, you're operating. Well, I'll back up. The concern of that is if you don't have a lot of suction head on a pump, it can create bubbles on the intake, and that's basically the energy added to the water from the pump is causing the fluid to turn to steam, and that causes bubbles, that causes cavitation. So as you can imagine, in a steam system, the water of the condensate is very close to the saturation temperature of water, and so even a little bit of energy added can cause that cavitation. And so it's actually beneficial on these low profile tanks to leave them uninsulated, as you're actually, by insulating them, you're kind of exacerbating the problem a little bit. The closer it is to boiling, the easier it is for that pump to cause the water to boil and cavitate. So anyway, that's the idea. So this is something that if there is enough head on the tank, if it's a tall tank and kind of a high operating point on the liquid level, then maybe it's okay. But a lot of times you want to leave those uninsulated. Also, flash tank atmospheric vents. So if you think about like a vent coming from, say, a tank like this, if you insulate the vent, then you're basically just helping the steam escape the system. So if it was to lose energy, it will turn back into condensate and possibly drip back down the vent, and then you're getting more condensate conserved. Maybe not a big deal, but it's just not, there's no benefit of insulating it unless it's for personnel protection. You also want to avoid, sometimes you can insulate like the head of a pump, but you want to avoid insulating motor housings and mechanical seals, unless it's like for freeze protection or something. But generally speaking, like especially in a steam system, mechanical seals can get overheated, and they need to reject that heat to atmosphere. So you don't want to insulate the whole thing. Air vents or anything that needs to breathe. Thermodynamic traps. Often you'll insulate a lot of your traps, but thermodynamic traps are designed to cool off through the cap. And if you insulate those, they can not cycle as much as they need to. And then you want to think about what you want to put removable jackets on. And that's basically anything that needs maintenance or testing, or might be prone to leaks, right? Like, so if you do it on, say, a flange set and it leaks, then you can pull the blanket off and check it out, instead of just having a whole section of permanent insulation, like just saturated with liquid and ruined. So yeah, a lot of good opportunities for removable insulation covers. So here's an example of an opportunity. There's a hospital with a central generation boiler plant and 10 buildings served. There was missing and degraded insulation in 3 systems, which was various steam line pressures from 5 to 80 pounds, condensate return lines, and hot water piping. Now here's an example of some of the steam piping that was uninsulated, or steam components, I should say. Here's the IR photo here. So you can see that this is kind of the before and then the after here. So you can see significantly less energy lost. You're still seeing some hot spots on the valve stems and things, but obviously a lot of energy conserved when putting those blankets on. The scope of work here, we had 206 instances of installation opportunities identified through an investment grade audit, retrofitted with 848 feet of conventional piping installation. Again, not all in the same place, just different like kind of patch jobs. Here's 5 feet, here's some fittings, like, you know, whatever was degraded, come through and fix whatever is deficient. And then also retrofitting like 132 pieces of equipment with removable insulation covers, which we call RICs, which is what we're talking about in the picture here. Another question: what is the view on insulation on devices near the boiler? Preserve all heat in the line, or is it preheating the combustion air to the boiler? Oh, I don't think that. So I get what you're saying. Like if you were to lose heat from components in the boiler room, that is contributing to preheating the combustion air in the boiler. I think so much of that heat is lost out of the room, though, through the walls and all, that I don't think you're getting. I think that you're getting a far less amount of heat that's being conserved in your combustion air than you are if you just kept it in the system. I would definitely recommend insulating all of your components and trying to keep that in the water side of the system, keep that heat in the water side of the system. But no, that's an interesting thought. Yeah, any heat that's lost to the room, you could be potentially recapturing, but then you're not really getting all of it. It's not making as big of an impact, and your combustion system is still inefficient. So I don't know. I think it's probably not even close. A hospital could have air conditioning savings from the insulation too. Yeah, that's true. And sometimes it's so you have to model like during the heating season, if you're reducing energy loss from your steam piping, then you're actually reducing the heat to the room, right? But it's still more efficient for it to go through the actual end users and be distributed to where it's intended to be distributed to. But you certainly see like you might see in a maintenance room or something where they intentionally took the insulation off of the pipe so that the room would be heated. Just kind of quick field engineering stuff like that. But yeah, that's certainly part of the equation. You're reducing air conditioning costs, especially in a system that is operating during the cooling season. Like if it's just in a K through 12 school or something, the boilers are off, right? So then you're not really affecting air conditioning. But if you're in a hospital, then it's on. So yeah, that's a good point. Anyway, annual savings here on this project were 10,365 million BTUs per year, about $129,567 annual value. That's a pretty specific number to say about, but that was the calculated savings. Typical installed cost for this type of job, $250,000 to $300,000 roughly. So payback of 1.9 to 2.3 years. That's a really good scope as well. And again, steam traps and insulation, like conserving your heat, getting the heat to where it needs to go, and improving the efficiency of the system. It also reduces maintenance and other things. So it just is, there's a cascading positive effects, I guess. This is another opportunity, pressure reduction ECM. This is can have big savings, like 2 to 8% savings if it's a good application for kind of a low cost scope. So if you're putting all these scopes in kind of enhancing the steam system efficiency, kind of bundled scope, this could be a good way to kind of bump up your savings a little bit. So the clues here that you have big PRV drops, you have a lot of low temperature loads, you have pinch control valves or overheating, distribution losses and long throttled mains, so like a long high pressure line and then it's throttled down and all the users are on low pressure and you're really only generating high pressure to get it through the distribution. And I should point out there too, like oftentimes with steam systems, loads are taken off. And so there may be less flow through the system than it was originally designed for. And so you have some room to increase or to reduce the pressure, even though it increases the velocity in the pipe and increases the pressure drop. You may be so far or far enough away from the original load that was designed for that piping that it may be okay. There's leak and vent losses, and that's from like higher pressure steam than required, like flashing when it goes to the condensate system. And then if there's downstream pressure margin. The concerns here, boiler water carryover. So increased velocity can out of the boiler can lead to entrainment of the boiler water, and that escaping into the steam system, which is called carryover, which can lead to poor quality steam. You can get like in an autoclave or something, you can get like spots on the instruments that are being cleaned and things like that. So and also can just lead to like erosion and damage of the piping. Other concerns: to increase velocity from the lower density steam now flowing much faster through the pipe. Increased pressure drop due to that increased velocity. Effects of reduced steam temperature. So if you're reducing the pressure that's actually supplied to your users, can those users operate well on a reduced temperature? The influence of steam pressure reduction on flow meter accuracy or other instruments and control valves. Effect of reduced boiler pressure on the boiler feed water pumps. Now that's specifically if you're reducing the pressure at the boiler. Reduced flow and lift capacity of steam traps. So the steam trap capacity is completely driven by the differential pressure over the trap. So if you reduce the upstream pressure, you may create condensate return issues. But there's a whole slew of savings. I won't go through all of them one by one, but generally speaking, if you reduce your pressure, you're reducing all of your losses. Any radiant losses through your distribution system, any leaks are now, leaking less. Steam traps, failed steam traps are now leaking less. You're spending less to generate the steam if you're reducing the pressure at the boiler. So it's just there's a lot of savings to be had, and kind of takes an engineering analysis to quantify all that and to vet out all the concerns. And that's probably the biggest cost of the scope, is just the analysis and trying to figure out what those savings are, and are all of those concerns vetted out that they're not going to be an issue. Okay, so backend development, kind of just a quick idea of what is the expected deliverables out of these reports. Again, we're just basing this on what we do, but I would think these are kind of generic outputs that you would expect. So for a steam trap test or survey report, we would provide a line-by-line Excel schedule with location, condition, recommended repair, replacement, cost savings, also all the details of the trap, like upstream pressure, downstream lift, trap type, model, make, operating pressure, just everything really that you need to kind of maintain and scope out a project for the failed traps as well. A written report with the detailed findings and recommendations, so kind of an associated write-up to kind of describe what we're seeing and support the Excel application schedule that we provide. And then, if applicable, scope and requirements for completing the trap monitoring system. So a trap monitoring system is a device on a trap, or it's a whole population of devices on all your traps, or at least your priority traps, that will monitor those traps and let you know if they fail. And there's different types of technology to do that, but it can really make sense if you have high fuel costs, high run hours, critical processes, or maybe constrained manpower on your maintenance team, right? Like you're just not able, or the facility is not able to get around and test and maintain the traps. Then you can put a monitor on it and let that monitor do it for you. And then there is a savings component there beyond just regular trap maintenance, and that is based on being able to respond to those leaks more quickly, right? It's like, so even if you do a yearly test and repair program, a trap could fail right after your previous test and be failed all year long. Whereas with a monitoring system, hopefully you can be responsive and address those leaks right away and mitigate more of the losses. And then usually through a steam trap test and survey report, we're going to see steam leaks and other deficiencies. Like I said, it is an opportunity multiplier. It's a great first step into development of scopes for a steam system. So it's just really kind of a good approach at almost any facility is to do a steam trap test and survey. Okay, so we're installation survey report, kind of same idea, line by line schedule of deficient installation opportunities, and a written report with detailed observations. And then for assessments and surveys, like an engineering assessment, generally this is like a whole system assessment where identifying any opportunities. Can be a targeted assessment, like say a pressure reduction engineering study or something like that. But basically we'll give an executive summary of the system conditions, loads, and efficiency, analysis of the steam distribution, all opportunities, pressure reduction, blowdown, anything that we see, and have a section for each opportunity with savings, opportunity description, rough order magnitude costs, and scope description. And then those are all summarized, and you can kind of rack and stack opportunities and see what makes sense. Yeah, that's kind of it. So it's basically like an engineering study if you're doing like a full system assessment. So that's it. So that in a nutshell, I mean, there's certainly exceptions to certain things that I've said, or different approaches based on specific needs, and we're flexible and can approach projects however it makes sense. But trying to describe it in general terms as how we approach surveys and walkdowns, and how you can use the clues that you see on those to identify opportunities, and hopefully you've learned like what some of those opportunities are. So thank you all for joining.